Okay, good afternoon. My name is Aaron Wallace. Like I said on my first example, I'm a master's student at Virginia Tech and I'm working on my final project, which is basically learning how to run simulations on SPARTA for doing direct simulation Monte Carlo and rarefied gas flows. So in the first example, we did the 1D coolant flow from section 12.2 of Bird's book. This example is going to be looking at section 12.3 of Bird's book, which is where he looks to determine the viscosity coefficient for different mixtures of helium and argon. So it adds one more at, and then the temperature he's using is at 293 Kelvin. So this adds one more level of complexity than the previous 12.2 example because now we have a mixture instead of a single gas. They're both still monatomic, so we don't have to worry about any rotational stuff with this. Um, One thing is he did use the variable soft sphere collision model in this one, where in 12.2 he used the variable hard sphere collision model. So let's just the setup is similar to what was done in 12.2. We'll go through the different files that are needed in the input file, and we'll look at the differences and where we have to adjust, and then we will run the program, do a quick post processing, and then just discuss it a little bit. My results for this, I would say, are fair. I have not been able to get as close um, to what Bird's results were as I would like. I found that on some mixtures it does better than others. So let's just get into it and start talking about the different files and how they've changed. All right, so we'll start with the species file like we did on the last example. And so now in this species file, we actually have two different species, which are argon and helium. So once again, you lay it out with this index here, and then the different parameters that you'll be using. Like I said, we're not going to be, this one doesn't include vibrational energy exchange or rotational energy exchange, so those aren't used. The species weight is still going to remain 1 for both of them because we're going to weight the simulation versus the real particles inside of the input script. So it's pretty simple here. You can Google the molecular weight. I rounded it off to the whole number here because it's very small amount that's being rounded, and that appears to be the ways they're doing it in all the examples in Sparta. So I did try it with the original like exact numbers, and it didn't really make a difference. Okay, so that pretty much concludes the species files. Nothing's really changed. We just have another species that we're going to be pulling into the simulation. Next, we're going to look at our collision model. And in this collision model, we're doing a variable soft sphere model, which we talked about. And so here we're going to be pulling different parameters from different tables. So the species or species pair, we have 3 different types of collisions that can happen. We can have an argon with argon collision, we can have a helium with helium collision, or we can have an argon with helium collision. All right, so for the diameter, we're going to look at table A3 of Bird's book, and you'll see if you looked at the last example, this number has changed a little bit from what we used in the variable hard sphere. The 0.81 is the same because, as we say, omega is from table A1, and it's the same for variable hard sphere or variable soft sphere. All right, T-ref is the same. Alpha, the scattering parameter. So now that we're not in a variable hard sphere, where alpha was 1, we actually have to look in table A3 and get the variable soft sphere alpha, which is the scattering parameter. And so that comes from table A3. So for species pair collisions, we have to look down in table A4 and get our omega and our alpha from there. It'll be alpha 1, 2 and omega 1, 2 in that table in Bird's Appendix A. And then for the diameter, the way Bird talks about it in Appendix A is you take the average diameter between the two. So this 3.205 e to the negative 10 is the average of these two diameters. So we're going to call this ID argon helium. And we pull these numbers from table A4. So that's the extra layer of complexity we have here. We have 3 different types of collisions when in the last example we had 1 type of collision. So now if we look in here at our input file, just like in the last example, we're going to initialize it as a 2D problem, even though it's quasi 1D, because SPARTA only allows 2 or 3Ds. The boundaries are the same. We got periodic on the X boundaries. We got a surface on the Y boundary for the upper and the lower surface, and then we have periodic for the Z boundary. We describe the surface collide just the same way. That way we're calling that upper boundary a surface, and it's diffusive in nature is the collisions, and this is the surface temperature. The surface temperature changed from the last example. In the last example it was 273, it's 293 in this one. We're still translating it for the upper surface 300 meters per second in the X direction. All right, this is all still just part of describing, telling SPARTA that these boundaries behave this way. Next, we go to the domain geometry. It hasn't changed from the first problem. We discussed that in there. If you are confused on this, just look back to that first example that I posted. The grid setup, it's the same type of grid. I just actually made it 220 cell widths in the Y direction compared to 200 in the last example. And it's 1 in the X, 220 in the Y, and 1 in the Z. Balanced grid is the same. Then we get down to our species and our gas mixture. This is where there's actually some changes. So our species now, we're pulling in that file for gas species, and we're telling it we need the information for argon and the information for helium, because those were the 2 IDs that we had in there. All right, so our mixture now is going to be a gas made up of argon and helium. The temperature of the mixture is going to be initialized at 293 Kelvin, and the velocity in the initialization is going to be 300 meters per second in the X direction. Now, here's where I've done something a little different than I did the last time, and you'll see it in a minute, but I'm basically stating that the number density is 1.4 e to the 20, and you'll see where that plays in here in a minute. Next, now this problem for 12.3, it goes over like 5 different mixtures that he did this simulation in, and one of the mixtures is 37.1% helium, and then the rest, of course, is argon. And you can see that's what I've done here by setting this mixture fractions up. So here's the particle weighting and initialization. This is something I did different in this simulation, which I probably could have done it the same way I did in the other. In the first example, but I'm trying to expand on how I use SPARTA. So I defined in row up here, which is the number density. So that defines the number of like particles that are in there. So when I get down here, I define F_num as 1.27 e to the 14. So that's F_num is how it relates, how many simulated or how many real particles are represented by a simulation particle. And I wrote down the calculation for this. You need these things. You need the in row, which we know we have 220 cells. We know we want 50 particles per cell. When I say our fake volume, that's because we don't really have a volume because we're in a quasi 1D state. It's always going to consider Z to be 1, and we actually have 1 in the Y direction, and then 0.1 is what we have in the X direction. So it's calculated as a volume, even though it's really not a volume because we're getting quasi 1D state. So if you do all these calculations, and it's laid out right here, you'll get F_num equals 1.27 e to the 14. This gives us 11,023 particles, which if you were to say you want 50 particles in 220 cells, you would get 11,000. So there's some in the rounding area there. It's giving me extra 23 particles. It's no concern. All right, so here I'm describing now, after I've made that calculation for what I want my fnum to be, I put it in here with the global command, and I say fnum is that. Then I say create particles, and I say we're going to create particles out of our gas up here, number of particles, and then if I put 0, it defaults to this in row and this fnum to figure out how many particles it's supposed to create, and that's when it creates the 11,023 particles. All right. Like discussed in the previous example, when we call the collide command, we're telling it we're going to collide in the VSS model. We're going to use this gas, and then our actual model comes from this file that we have saved that we discussed a minute ago, where we looked at the different types of collisions that can happen. All right. Nothing has really changed from the last example about how to do the computes. Go back and look at that example. We'll do a little more talking on that. We did a lot of talking on the computes and the fixes and the dumps in the first example. We're going to kind of breeze through that now. One thing is here you can see where I've got a different type of compute or a different type of fix in here where it's doing averages. Doesn't matter because this is actually going to get tossed, and because we're not going to use this for the steady state. All right, so output files, this will only be enabled during the steady state model, but this is going to get fixed again too. This really could be removed from the this fix and this dump section could be removed from the file if you wanted. All right, statistical output, this is the same, where you can watch it as you're progressing down through in the command line and see what's happening. Its time steps are the same. I'm using a little bit different number than Bird used for the amount of steps in section 12.3. I noticed during while running the simulation a bunch of different behaviors, and one thing is it's got a really strong undershoot, and then there's a lot of statistical scatter in here. So I tried to push really far out, make sure that I'm in the steady state, and then I'm going to start taking my data. And I'm taking my data in the same way in the steady state that I did in the last problem. So when I get to the end, I'll have a running average over this 100,000 time steps. But I noticed in the beginning, even if it wasn't at steady state, there was so much statistical oscillation that I wasn't able to get a good running average. So I just pushed it out, and then we'll run 100,000 afterwards. Even in his 12.3, he runs the simulation much longer than he runs the simulation in 12.2. All right, so you see that everything is laid out. So we will go back here, and like we did before, I'm going to open in the terminal, and then you'll see I've got it named nCoolIt Bird, so that's what you put there. And then MPI run, I'm still using 2 processors, telling it how to get back to where this is, the SPA MPI program is. Run it, and you can see we got 11,023 particles. Everything's staying kind of stable. So everything's looking good. This actually takes a good little bit of time to run. 3 or 4 minutes. So I think we can go ahead and just leave this here. And I've ran it already. Like I said before, you got to really look down through this stuff. One thing I didn't talk about in the last example is when you do make your post-processing program, you can have Python read this in as a text file, then have it convert it to a CSV file, and there's programs out there that'll color code it to where everything in one column runs the same color. It makes it a lot easier to read. But that's where we are on that. And so we switch over here. I built a post process, and this one is not nearly as robust as the first one. It just does some calculations, and as you see, it has one plot, and this just is a velocity plot, just so a common sense check. Yeah, we got our slip. The velocity is about what it's supposed to be, so it just gives me something to say, yeah, I do have something that's running moderately correct. And then you see when I do do this down here, I put in what Bird had for this mixture, and he got 2.31 times 10 to the negative 5 for his viscosity coefficient here, and then Sparta's giving me 2.27. So I got a 1.7% error from what Bird had, and I would hope, I would like it to be a little closer. I could live with that, but some of the other mixtures, it seems like it's better. Some of the other mixtures, it seems like it's worse. All of the results I got were around within 5%. But if somebody can see something that I'm doing wrong, please feel free to speak up. And maybe I'm forgetting something in the physics that is causing me to be um, different than what Bird got in 12.3. So I think this kind of breaks it in, and it adds one more layer of complexity to the problem. So it's another building step on the first example we did. And the next example will be building. It'll be building in a different direction. It'll be a 2D problem, and it'll only be one gas, but it'll be a diatomic gas, so it'll add some extra complexity there. But anyway, thanks again for watching. I hope this helps somebody, and feel free to comment. And if you have something constructive, or if you're some question, like I said, I'll try to answer it. But anyway, my name is Aaron again, and master student at Virginia Tech, working on my final project. And have a good day. Thank you. Bye.